Okay, so our project is about determining the status of epoch 2015344540 with AutoVAR. First thing is detecting exoplanets using the transit method. And you can do this by looking at the light curve of a star. And a light curve is basically the phase of a star versus the differential magnitude. So when an exoplanet passes in front of a star, it will, the amount of light seen, some light is blocked from the star. And a very common type of exoplanet is because they're very large, hot Jupiters are easy to detect. So next is an eclipsing binary, which is very similar to an exoplanet transit, and you can detect it by looking at the light curve of a star or a binary star. And with binaries, the light curve will not just have one dip, but it'll have two, one where the secondary goes in front of the primary and where the secondary goes behind the primary. So our star, epoch 2015344540, is both a candidate for a exoplanet and for an eclipsing binary. So if we look at its light curve, it's hard to determine whether it's a hot Jupiter or if it has a brown dwarf.
Okay, so in order to understand this, so the secondary radius of the radius of the secondary body is 0.37 solar radii, which puts the secondary body straight in the middle between a brown dwarf and a hot Jupiter. So that is one challenge that makes it difficult to ascertain whether it's an exoplanet or an eclipsing binary star, and its orbital period is about 2.72 days and 0.053 AU, which is awfully close. And then the star type is it's a type A star, which puts it straight in the middle of an HR diagram based on its luminosity and temperature. And here's an HR diagram with an example. So as you can see, it is slightly tending towards the hot and bright area, but however it is fairly in the middle. And then following on to the secondary dip. So the way to detect it. So based on looking for a secondary dip in an eclipsing binary, it's this secondary dip is possibly there, but it isn't. But it's very hard to tell due to the presence of noise.
Okay, so the AutoVAR algorithm was developed by Michael Fitzgerald and in Python, and it's designed to measure exoplanet transit. And it works by creating a megacomp star, which basically combines low variability stars into one and considers their summation of their ADU counts and takes them in aggregate. And this averages out any error that any one comp star would have. There might be 6 stars in our megacomp. We tested our case with WASP-43, which was discovered by Helier et al. In 2011 to be an exoplanetary system. The model test case because of the large size of the flux dip. So Helier's data is on the left, our data is on the right, and our data calculated with AutoVAR is on the right, and it clearly demonstrates an exoplanetary dip. So saturation, we have to deal with saturation a lot, especially the debate of whether to have a longer exposure time and thus improve the quality of our results, but risk image saturation, which totally ruins our data when a saturation bleed, as shown on the left, occurs when a pixel has too much light in it. And this is an incredibly preliminary light curve that was measured using very preliminary data.